Hello, my name is Yun-Jhe Jiang, and I am currently pursuing my studies at the National Taiwan University of Science and Technology under the guidance of my advisor, Xiaoyun Fang. I am excited to present to you the topic of pin access-oriented concurrent detail routing, which proposes a solution to address the issue of pin access in the detail routing stage using an ILP formulation. Here is the outline. I will give the main contributions of our proposed pin access-oriented detail routing and provide an overview of the overall flow. I will discuss several key techniques utilized in PACDR, including constructing a connection tree, performing redundant metal trimming, inserting auxiliary metal, and using R-tree spatial clustering. I will also cover the PACDR ILP formulation, a mathematical model used to optimize the routing process. Finally, I will present experimental results that demonstrate the effectiveness of PA-oriented concurrent detail routing. Due to the continuous scaling of technology nodes, the reduction in feature sizes and increase in standard cell density have led to significant pin access challenges. This has become a major obstacle to achieving high routability, ultimately slowing down the design closure process. Previous studies have typically employed metal two-wire segments to create design rule-free pin extensions, which aim to enhance pin access probabilities. Figure B illustrates 4 pin extensions with metal two segments from the original cell in Figure A. Additionally, Figure C depicts a traditional method for detail routing post-track assignment. Despite its effectiveness, the extension method has several limitations. For one, the segments created during this method cannot be fully utilized during the detail routing stage and ultimately limiting the solution space. As we compare Figure B and C, we can observe that having more than one access point in a pin is a common practice. This helps avoid issues such as longer wire length and design rule violations, as seen in pins B and D. The pin access-oriented detail routing method has been proposed to effectively address these limitations. In a previous study cited as reference 4, a similar approach was proposed to address the pin access problem using a multi-commodity flow-based ILP formulation. However, that study did not delve much into the steps taken between track assignment and detail routing. In this paper, we outline the various steps involved in the pin access-oriented detail routing method, which includes shortening or removing redundant metals, inserting auxiliary metals to simplify complexity, and clustering related routing nets using an efficient R-tree algorithm. We also address some of the shortcomings of the ILP formulation proposed in reference 4. For instance, we automatically determine standard points and differentiate between different obstacles for different nets when dealing with multi-pin nets. In contrast, the previous study simply chose a standard point and treated all nets as separate entities, regardless of whether they were the same net. As illustrated in Figure A, some connections require completion during detail routing. With our ILP formulation, we can effectively determine a proper standard point for multi-pin net C. Additionally, we do not consider net B's wire segment as an obstacle, allowing for greater flexibility in the routing process. Furthermore, we transform the routing model into an undirected routing model, which reduces the complexity of the ILP formulation. The overall flow of PACDR is depicted in this figure, with the input being a left file of technology information and a ZAP file describing the track assignment results. To obtain the ZAP file, we utilize the commercial tool Innoverse for cell placement and an open-source detail router, Triton Route WXL, while adopting the 7nm standard cell library to consider pin layouts in advanced process nodes. The flow of PACDR begins with initialization, followed by the trimming of redundant metals and insertion of auxiliary metals to keep the problem size tractable. In the triple connection routing stage, short connections are routed first with simple heuristics, and then the remaining connections are clustered by an R-tree spatial clustering approach. Finally, the pin access-oriented concurrent detail routing is performed for each pin cluster using an ILP formulation. In the initialization stage, we find connections from pins to segments derived from the track assignment stage. In the initialization stage, a method is proposed to identify the segment to which each pin connects. An example with 6 pins and yellow segments is presented in the figure. To achieve this goal, the idea of constructing a minimum spanning tree is used. The resulting minimum spanning tree is used to classify the connections between pins and segments into 4 categories, namely instance pin to segment end, instance pin to middle of segment, instance pin to segment corner, and instance pin to instance pin. Wire segments are assigned during the track assignment stage based on global routing results. In addition, some short segments are usually assigned to reserve routing resources for specific pins, which is beneficial for conventional detail routing, but not for PACDR. Therefore, as a pre-processing step, overlength or redundant wire segments are removed or trimmed to make space for PACDR. The segments are classified into 3 types: over-assigned, assistance, and pass-through. Over-assigned segments are shortened, assistance segments are removed, and pass-through segments are preserved for PACDR. The bounding box that encompasses the pin and the segment point of the connection is known as the free routing space of a connection. The objective is to complete the detailed routing of each connection within its free routing space. To simplify the problem complexity, it is important to keep the free routing space as small as possible. However, the connection of 2 pins of different cell instances, which is referred to as a type 4 connection, can result in a larger free routing space. To overcome this issue, our strategy is to insert an auxiliary metal and divide a large FRS into 2 smaller ones. This approach helps simplify the problem and reduce the runtime required by the ILP solver. In order to solve the pin access problem concurrently, it is necessary to identify which free routing space should be considered together. To achieve this, we employ an R-tree-based spatial clustering approach, where the cluster connections whose free routing spaces overlap with each other. This method involves querying the overlap free routing spaces with R-tree and then clustering the overlap free routing space recursively. Compared to the traditional approach of comparing every pair of free routing spaces, this method has a much lower complexity. Our proposed ILP formulation aims to solve the problem of undirected graph-based multi-commodity flow. The formulation is designed to handle both single and multiple resources and targets which are unified as a super vertex. The formulation incorporates 2 types of edge constraints, super edges and basic edges. The total flow on the neighboring edges of a supervertex is set to be 1, which ensures that at least one access point is used for the source or target. The basic edge constraint determines whether a connection passes through a vertex or not, and the total flow on the neighboring edges of a basic vertex is either 2 or 0. To determine if a connection passes through a vertex, we check if any neighboring edges to the vertex is used by the connection. If any edge has a flow of 1, then the flow of the vertex should be also 1. To simplify the nonlinear constraints in equation 4, we utilize the vertex variable from equation 5. By doing so, we transform the constraints into equation 6, which is linear and can be solved more efficiently by our ILP solver. In equation 6, if the connection doesn't pass through the vertex, then the total flow on the neighboring edges is 0. Conversely, if the connection passes through the vertex, then the total flow on the neighboring edges is 2. The use of an obstacle map in our ILP formulation allows for the differentiation of obstacle based on various nets. This map aids in identifying the specific obstacle for each connection, thus enabling the routing of the same net while rendering other nets unroutable. Figure A demonstrates that net B, which includes its pin and segment, is considered routable, while the pins and segments of other nets are deemed obstacles. By comparing figure A and B, we can see that the obstacles vary depending on the net being routed. By comparing figure A and B, we can see that the obstacles vary depending on the net being routed. To prevent connections from passing through obstacle vertices, we designated the neighboring edges of each obstacle vertex with a total flow of 0, effectively treating it as an obstacle. When multiple nets are being concurrently routed in a free routing space, the usage of edges is taken into consideration. We assume that the same net routing can share the same edges, while different net routing cannot share the same edge. To achieve this, we write a nonlinear function equation A with an OR operator. In this equation, B and C represent the same routing net, while D, E, and F represent another same routing net. However, to make it easier for the ILP solver to solve efficiently, we divide equation 8 into 6 linear equations. This approach ensures that the ILP solver can solve the problem more effectively. Minimizing the sum of every routing net is not a straightforward task because there are several edges shared within the same net. To address this issue, we can unify the total metal usage to solve the problem. The physical metal usage constraints indicates that if there is more than one net sharing an edge, the edge should only be counted once. By minimizing the physical metal, we can obtain an optimal solution. Using our ILP formulation, we can effectively determine a suitable center point for a multi-pin net. Furthermore, we consider a suitable obstacle for every routing net, which provides greater flexibility in the routing process. The first experiment involved a comparison of variables and constraints between the undirected and directed routing models, with each test case named based on 3 dimensions x, y, and z of the routing plane. The findings indicated that undirected routing model demonstrated a reduction of 42% and 41% in variables and constraints, respectively. The second experiment involved a comparison of the initial detail routing results between the proposed PNCDR method and Triton Route WXL. In the ISPD 2018 test case, Triton Rail WXL was found to have an average of 3 times more design rule violations and took 11 times longer on CPU time compared to PACDR. This is the end of my presentation. Thank you everyone for listening.